Good morning, everyone. We will start with one of the most important applications of convective heat transfer, that is boiling heat transfer. Boiling heat transfer and condensation heat transfer come under the broad category of two-phase flow and heat transfer, and as we have seen in single phase convection, both flow and heat transfer go hand in hand. More so here because you have both change of phase as well as convection contributing to the overall heat transfer mechanism. So, what do we mean by boiling? Boiling, evaporation are these two terms which people use many times interchangeably without knowing, but evaporation primarily is a surface phenomena where if you leave a cup of water or saucer of water open for a couple of days, after a few hours the amount of liquid in the saucer reduces. This is primarily because of evaporation, even though there is no heat transfer. It is going to happen because of the concentration difference between the water and the surrounding, and that is why clothes do not dry well in monsoon season when the humidity level is very high. We are going to restrict ourselves to boiling heat transfer, and this is by no means an exhaustive course on two-phase flow. This is just going to be a couple of hours of introduction and some terminology that people need to know when they are dealing with boiling heat transfer. We would also try to cover different aspects of boiling heat transfer which make it very unique compared to single phase heat transfer. So, when we think of boiling, the first example that comes to mind in everyday life is boiling of water for tea. And tea or coffee or whatever, when you are going to boil water, there are a lot of things that happen that many of us have noticed, many of us have not noticed that often, but it is something which happens every time. And you would see that if the gas flame is kept low and you have a vessel of water, the way the water boils is very different from the way the water boils when you have the flame kept at a high value or when the flame is on high. So, you tend to see sudden bursts of bubbles etc., when you have high flame, whereas when we have a low flame you can see many different fascinating aspects during the process of boiling. So, this couple of hours of the topic on boiling will introduce us to the classification of boiling, the terminologies used in various mechanisms that occur. Most importantly, the boiling curve, which is a graphical representation of the heat flux versus the wall superheat, which in turn gives us the slope or the heat transfer coefficient associated with boiling heat transfer. And we will talk a little about what each of these terms mean and how they can directly be used in understanding boiling heat transfer. So, the first set of slides that I am going to show are basically the topics that we are going to cover. We just will have a brief introduction. We will talk in detail about the boiling curve. We will talk a little about pool boiling and flow boiling and give about a short description on what is critical heat flux or burnout, which this is grossly misunderstood many times. So, I would like to spend about 15 minutes on this very important topic also. So, what is boiling heat transfer? We have seen through the last 5 minutes what boiling would be. Boiling can be broadly classified as pool and flow boiling. Now, as the name suggests, pool boiling, in single phase convection, we had what was called as natural convection and forced convection. Natural convection was primarily where you had density difference caused by temperature difference causing the heat transfer. Delta T was needed in both cases. Where the flow was being forced, we called it forced convective heat transfer. Where the flow happened because of density difference, we called it natural convection. Now, here in boiling heat transfer, we have two broad classifications, one is pool and other is flow. Pool boiling is what you essentially see when you boil water for tea. Okay, boiling water in a kettle, or you have these storage water heaters that are there in the bathrooms, where you fill the tank, fill the heater chamber, have electrical current pass through a coil, and that heats up the water for you to for bath. And this need not give rise to steam many cases, but our applications here are where there is a change of phase necessarily. Okay. Flow boiling, on the other hand, is basically what you would see in devices, in equipment called as evaporators or condensers, which is opposite of boiling, where there is condensation of steam to liquid water. So, the big difference between the two is, in one case, in pool boiling, there is a stagnant pool of water, there is no bulk movement of the water. So, why do we study pool boiling, even though bulk of the engineering applications involve flow? Heat exchangers, condensers, steam generators. As the name suggests, steam generator is nothing but a heat exchanger where steam is being generated. Okay, so there are different names given to specific applications. That is why you would call something as an evaporator, something as a steam generator, but broadly speaking, everything is a heat transfer device. So, what is the broad definition of any heat exchanger is where heat is transferred across a solid surface to a working fluid, and there could be change of phase, or there could be just increase in sensible heating. So, flow boiling is where the bulk of the action in real life is. Then why do we study pool boiling? Pool boiling is very important because pool boiling involves one less variable which causes lot of difficulty in analysis, and that is flow. Fluid mechanics of flowing water is lot more difficult than stagnant pool. And when we talk of boiling, the primary reason why boiling is so much better compared to single phase heat transfer is the removal of the latent heat. So, for the same temperature difference, you get a higher heat transfer coefficient. Now, in basic thermodynamics, we would have seen the following. So, if all of us have access to basic thermodynamics textbooks. In case you don't, you can take a look at this from the internet also. We have what is called as a PV diagram and a TV diagram, and that essentially was given to us by a dome like this. And if I draw the V axis here, and this could be P or T, let me take it as TV diagram. And what happens in a TV diagram is essentially you have a thought experiment which was done where you had a certain mass of water whose temperature was kept at 30 degree. Progressively heat was added and the pressure maintained constant, and you would see how the specific volume increases progressively until the temperature became the saturation temperature. At saturation temperature, if you added more heat, this would happen. The increase in specific volume would be there with no change in temperature, and after you reach complete conversion of all the liquid in the chamber to steam, the temperature would further rise. And this was what was called as the steam dome, and the regions would be liquid plus vapor here, superheated vapor or vapor alone here, and this would be called as subcooled liquid. This we have seen in basic thermodynamics, and in this region you needed an additional quantity called thermodynamic quality, which is given by the symbol X, which was necessary to identify whether I was in this location or this location. This would be a low quality situation, 0.1 here, 0.2 would be a higher quality situation, and both of these cases, state 1 and state 2. State 1 is at P, this is P equal to constant, P and T sat x1. State 2 on the other hand is also at P, T sat, but thermodynamic quality x2. The difference in these thermodynamic quality values makes these two states unique, and the amount of heat added between state 1 and state 2 is responsible for conversion of that much amount of liquid to vapor. So, we all know this. So, if you take a small control volume, all of us know what a control volume is. If this is a pipe through which liquid is flowing, and this is a control volume, by which I mean a region fixed in the flow field through which all the activity is happening, and you are going to just see it. So, if I have heat coming in this way, let us say this is a constant wall heat flux situation, and if m dot is the mass flow rate, and if this is coming in at some temperature T bulk mean, and my control volume element is of thickness dz. I use z on purpose because x is used for quality, and here exit of the control volume you have Tm plus dTm, and m dot again is going out. Properties are constant, Cp is constant over the range of temperature, and if I do a basic energy balance, it would mean E dot in minus E dot out plus E dot generated is equal to E dot stored. This is my basic equation that you would have studied in heat transfer, and my list of assumptions here would be steady state, constant properties, okay, constant properties, heat flux is constant, this is constant m dot d, everything is constant. This is a circular pipe, or you can have any cross section, the flow area is constant, basically mass flow rate is also constant. No volumetric heat generation, by that I mean you do not have chemical reactions or some kind of exothermic stuff where you are going to have additional heat generated. And if I use these assumptions and simplify the energy balance equation, because of steady state this is going to drop off. There is no volumetric heat generation, so this is going to drop off. This is because of assumption 5, 1, 2, 3, 4 and 5, and E dot in is equal to E dot out, and if I write the energy balance for this control volume, it would be m dot Cp T bulk mean in coming in plus q double prime pi d dz if it is a circular pipe minus m dot Cp Tm plus dTm equal to 0. This pi d dz for other geometries can be replaced by perimeter P into delta z, and if I simplify this, I would get m dot Cp Tm minus m dot Cp Tm plus q double prime pi d dz is equal to m dot Cp dTm, and this simply gives me dTm by dz is equal to q double prime pi d by m dot Cp. So, this is a simple first order ordinary differential equation which tells me how temperature is going to vary along the length of the pipe or along the flow direction. This is my z direction, flow direction, and if I integrate this, I can just get a temperature at any z is going to be temperature at inlet plus q double prime pi d z m dot Cp. It is a very simple but powerful equation which can be used. This is already done in single phase heat transfer, where bulk mean temperature distribution was obtained in internal flows. This is for single phase, and if we plotted this, we would very nicely get T as a function of z. I would have what is called as the entrance region, and you have drawn this also, T bulk mean as a function of z, and wall temperature would do this, and for constant wall heat flux case the temperature difference delta T is going to be constant. This all you have seen. So, this is all for single phase. Now, what is different in two-phase situation? Two-phase situation, you are not going to have T changing to T plus dTm. Look at this, you are now at state 1, which is at quality x1, you are going to a state 2 where quality is x2. So, instead of writing the energy balance for a single phase fluid, so energy balance now is going to be written for a two-phase substance coming in, E dot in minus E dot out equal to 0. The assumptions remain pretty much the same. Constant properties means pressure drop is negligible. So, saturation properties do not change, and we can assume that the saturation temperature remains the same. Now, what is the difference here? So, if I take this control volume, the same rectangle of thickness delta Z or dZ is going to be m dot coming in and enthalpy H, and here the fluid is going out with m dot H plus dH as opposed to Tm and Tm plus dTm. So, when I use this control volume for my analysis, I am going to write the energy balance as m dot H, enthalpy of the fluid coming in, plus the energy added pi dz q into pi d dz is equal to m dot H plus dH, and this on simplification gives me dH by dz is equal to q double prime pi d by m dot, q double prime pi d by m dot. Okay. Unlike the single phase situation where you had dt m by dz is q double prime pi d by m dot Cp, you have rate of enthalpy change along the flow direction. The gradient is nothing but q double prime pi d divided by m dot. Okay. Now, how do I bring quality into this? We know that H is equal to Hf plus x times Hfg. So, dH by dz is equal to Hfg into dx by dz. This is where the assumption of constant properties become very important, because if I say properties are constant, derivative of saturated liquid enthalpy, derivative of Hfg with respect to z along the flow direction is 0, because properties are assumed constant, and this when I substitute here, I would get dx by dz is equal to q double prime pi d by m dot Hfg. I hope you are able to see this. Now, for single phase we had q double prime pi d by m dot Cp. How does temperature vary along the flow direction? How does quality vary along the flow direction is given by this. How does quality vary? So, if I have fluid coming in at quality x1, x at z2 minus x at z1 is equal to q double prime pi d m dot Hfg into z2 minus z1. This is what was used when we did basic thermodynamics. In fact, I do not know whether you remember, you would write it as x is equal to H minus Hf divided by Hg minus Hf. This was your definition of your thermodynamic quality, and at state 1 it would be a enthalpy value corresponding to state 1. If you were given the value, you would find the quality, or if you were given the quality, you would find the enthalpy appropriately. Now, why I said all this is that in a regular steam generator or evaporator, the governing equation for variation of quality is this. If I have constant wall heat flux, then this expression can be integrated like this. If there is a variable wall heat flux, then dx by dz is equal to q double prime pi d by m dot hfg. We have to keep the q double prime inside the integral. So, x2 minus x1 is nothing but pi d by m dot hfg integral z1 to z2 q double prime, which is a function of z dz. So, fundamentally nothing changes. The complexity of the integration depends on the complexity of the function given. If you have variable properties, then this also would not come out, it will be inside the integral, and you would have to have an expression for the latent heat HFG as a function of Z, which in turn would be a function of pressure. So, it is a very involved exercise, but bear in mind, however complex the problem is, the complexity changes only in how the mathematical treatment happens. Fundamentally nothing is going to change, it is just that your equations become a little bit more complex, your equation take a little longer for you to solve. What goes on for 2 pages would probably take 8 pages, but apart from that there is no great change, and lot of bookkeeping probably is needed. So, flow boiling, as you see, involves some aspect of thermodynamics which we have already studied, and boiling in a heated channel is what is commonly studied. By channel I mean a pipe or a flow path where there is transfer of heat across a solid boundary. This could be you call as evaporator, steam generator, or a rod bundle in case of a nuclear reactor. In a nuclear reactor, you have something called as a rod bundle, which is essentially a bunch of fuel rods. I am going to show you the top view. A fuel rod bundle is something like this. A simple example or analogy is where you have these crates where you get this cool drink, thumbs up and things like that. You have the thumbs up, think of them as the rods. The crate is something which holds it in position, and there is space between these rods through which the flow is going to happen. So, if I show this as a 5 by 5 rod bundle, 5 by 5 means 5 by 5, 5 this way, 5 this way, 25 rod cluster, and of course, there are other things to protect this and things so on and so forth. But from heat transfer boiling point of view, you are talking of a flow which is either going into the plane of the paper or coming out, and this is a solid heater rod. Flow is happening through this path. These are all solids. These 25 circles are there, which are nothing but heat generating surfaces. Because of nuclear reaction, heat is coming into this fluid, into this fluid, into this fluid, everywhere. So, these are what are going to generate heat, and the flow is happening through into the plane of the paper. So, even for a complex situation like this, a simple pipe flow analogy is very easy to use. Why? Because you use the concept of hydraulic diameter and try to convert each of these spaces, each of this flow paths into an equivalent circular pipe geometry with the heat being distributed around the periphery, and you use the results that you obtain for circular pipe geometry very easily for even a complex geometry like rod bundle. Of course, what you predict using circular pipe geometry is not going to be what happens here. There are several aspects like cross flow happening between these two paths, cross flow this way, turbulent mixing, etc. So, there are correction factors which would be used. The point I am trying to make is, even though there is a very complex two-phase problem, boiling problem, a simple pipe flow solution, pipe flow method is what is applied with a lot of correction factors. So, fundamental studies are always going to be useful no matter how complex the geometry is, and that is why flow boiling in a circular pipe is very important for us from understanding point of view. So, let me go back to the slides here. So, flow boiling, as you see, a boiling occurring in case of fluid flowing through a heated channel, which could be pipe, evaporator, flow, or a rod bundle geometry in nuclear reactors. Flow boiling heat transfer coefficient is slightly higher than for pool boiling because of the flow. Remember, in natural convection versus forced convection, the heat transfer coefficient in forced convection was much more, and that much more aspect came because of the bulk flow velocity involving a non-dimensional number called as Reynolds number. Same thing here, pool versus flow boiling, we would have a higher heat transfer coefficient for flow boiling as opposed to pool boiling. Most engineering applications, as I said, involve flow boiling, and we are going to study pool boiling, or we are going to talk a little about pool boiling because understanding of the concept of boiling happens when we remove the velocity aspect, when we talk only of a stagnant pool, because that convection aspect which was there, when it is removed, you are able to study how a bubble is formed, how it is coming out of the surface, how fast it is coming, one bubble after the other. Does it come simultaneously, or is there some time lag between one bubble and the next? All this fundamental study is possible when I have removed the aspect of velocity, flow velocity, which is very important in flow boiling, from it. So, I have pool boiling where fundamental studies are done, we have flow boiling where applied studies get done. In the next module, we will just talk a little bit about the boiling curve. I will present the boiling curve and its salient features, and we will take the subject matter from there. Thank you.